Reset rebuilding civilization. What would happen if our present civilization were to collapse? And then, the reconstruction of the civilization that vanished. That is, we will try designing a civilization. Whether our current way of life and civilization are actually good for us. Or, when it comes to the question of whether they might be poorly made, we have no yardstick, nothing to compare them against. Whether the civilization we hope for, or idealize, would bring good results or bad. And furthermore, whether it benefits me, us, the family, the nation, or the earth, we can't judge anything without seeing the outcomes. One way to design a civilization for which no such scale exists is science fiction. Because running physical social experiments is extremely costly, thought experiments like SF are a very effective means. Or, you can think of SF as having that role. And it's fine to think of it that way. The thought experiments offered by anime or sci-fi dramas, together with the simulated experiences through visuals, provide us with a major yardstick. In the real world, when designing civilization or everyday life, there are obstacles we clearly understand. Namely, the fact that we can't get away from maintaining, altering the status quo. Or, in other words, a tendency that constrains our thinking. Humans already depend on existing science and technology, culture and civilization, and we depend on them strongly. This is not about science or civilization themselves, but rather about the current science and civilization. And there is a clear reason for this dependence. It's the human stance of maintaining, revising the status quo. In short, a strong force toward the status quo acts on us. Humans have trouble taking interest in distant changes. We're attuned to small changes, what happens in a few hours tomorrow, to things close at hand. Accordingly, a strong force for the status quo prevails. This is our dependence on the current civilization. This is a good thing as well, but conversely, even if there are problems, it is also a force that tries to preserve those problems as they are. As a result, even if for humans, a sweeping transformation of civilization were extremely beneficial, we would not carry it out. Furthermore, that also robs us of our creativity. So, from a situation where civilization has disappeared by running a simulation to rebuild civilization, the idea is to try to accelerate that creativity. What emerged in this inquiry is the reason we rapidly developed civilization. When we talk about why civilization and science advanced so quickly, that expanding civilization is a universal human trait, for example, or that when a certain time arrived, the knowledge and techniques that had been slowly accumulating blossomed, and that period was the Industrial Revolution, we tend to think that way. But why was the Industrial Revolution at that timing in the 18th century? And why did it occur in Britain? The reasons, that is, the mechanism, come to light. To state the conclusion, the Industrial Revolution would not have been strange if it had occurred in the 14th century, is also what we come to understand. If you confuse purpose with goals, you can't push your efforts to the limit. We'd already be well past the singularity. We might be immortal, zipping around the universe. I digress. But in considering whether a civilization is good or bad, the best method available now is thought experiments. Moreover, even if we were to run a thought experiment based on maintaining or revising the existing civilization, a bias to preserve the present would inevitably come into play. Therefore, this time, after civilization has once perished, we'll assume only rough basic knowledge, science, history, and the like. The kind of knowledge every elementary or junior high student has, and consider what kind of design we'd get if we rebuild civilization with only compulsory education level knowledge. The specifics of how civilization perishes aren't the point today, but when rebuilding it, we need to set the conditions under which that happens. So I've prepared two scenarios. One, civilization vanishes without a trace, and we rebuild from almost zero. The other, immediate rebuilding after a mass die-off. As a story about civilization disappearing completely, I think a story inspired by Planet of the Apes is just about as realistic as it gets. A few dozen humans go on a space mission, travel at sublight speed, and when they return, say, about 2,000 years have passed. Artifacts return to the Earth, with no trace after as little as 200 years. You may be surprised, but even sturdy human-made structures do. Metals and plastic products, without human maintenance, are quickly broken down, shattered to the molecular level. As soon as humans are gone, plants start invading within months. Buildings, roads, even things like cars. In a year, water seeps in through cracks, the sun beats down, temperatures fluctuate. Under that, things lose their shapes at a tremendous pace. It proceeds at a speed beyond imagination. Most products derived from petroleum would be broken down by microbes in no time, and abundant metals like iron would oxidize and decay, turning into sand or rock and the like, or becoming nutrients for plants and microbes. Accordingly, the traces of civilization we've built up are mostly lost in about 200 years. Keeping artifacts intact requires meticulous upkeep and labor. The other scenario is a pattern of mass human extinction. A nuclear war could drastically alter the environment, so suppose someone, with intent, attempted to wipe out only humans using biological or chemical weapons, or something like a neutron bomb, leaving only a few to a few dozen people. Even in this case, modern civilization would quickly become unusable. For example, GPS, once it can't be controlled from its command centers, stops functioning in no time, and after 2 weeks the errors keep growing, degrading to about 500 meters, it said. After 1 month, the errors spread so much, it's essentially unusable. I myself am not particularly interested in extinction stories, but realism is better, so I'm using these two as settings. In either story, you may come to realize just how complex our civilization is. Over the last 10,000 years or so, we've learned to act as organizations and to divide labor. And with modernity producing diverse industries and growing more advanced, we've come to rely on human organizations, that is society, for most of what we need to live. Put differently, aside from our small personal roles, we live by using tools and services made or devised by tens of thousands or even hundreds of millions of other people. As things stand, we don't worry about how to procure tomorrow's meals. Right after rebuilding, we'd need food, clothing and shelter, and even just securing food with a small number of people and no scientific civilization would likely mean such hard work awaits that we'd have to devote all our human resources to obtaining food. In the second scenario, where recovery occurs immediately after extinction, a huge amount of human assets equivalent to 7 billion people would be involved, so there would likely be a grace period of several years to several decades. But if it's the first case, with not even traces of civilization left, we'd be in for tremendous hardship. Having no grace period means the costly work of securing food and other necessities for survival will absorb our resources, leaving no time to rebuild a scientific civilization. If a scientific civilization's remnants remain, canned goods, grains, clothing and the like would cover us for a few years, but most of what humanity left will return to the earth in no time, so you'll need to collect and manage it immediately. As for grain seeds, you absolutely must secure them. It may not be obvious, but crop seeds compared with other technologies take extremely long to re-establish. Alongside that, gather as many reference materials as possible, field guides, textbooks, especially in the basic sciences. If resources allow, in applied sciences or medicine as well, anything that could prove useful later might be worth collecting. If the scientific civilization has vanished completely, you'd gather nuts, acorns and fruits and the like, and basically spend a while living by hunting. Probably the easiest would be hunting aquatic creatures. This time, rather than survival per se, the goal is designing a civilization. So in this case it's better to consider a world where the scientific civilization is gone, as that should remove more bias. From here, I'd like to think about rebuilding civilization in a world where the scientific civilization has disappeared. At the present moment, resources still exist in abundance. In a world where civilization has vanished, we'll face the difficulty of obtaining resources. That's because, even today, there are hardly any resources left that are easy to extract. The resources that are abundant now are those obtainable only through advanced industry and science. Therefore, in a world without such technologies, acquiring the kinds of resources humanity uses now is extremely hard. Until you develop some mining, transport, and scientific capability, it will be quite a struggle, and you can't rely on them. Besides stabilizing food, clothing, and shelter, and ensuring security when civilization disappears, there's something we must actively do. That is securing manpower. Behind human vitality lies intelligence, and what multiplies that power many times over is organization. In short, in the early stage of rebuilding, the most important mission is to raise many children and educate them. As I touched on earlier, with a population of only a few to a few dozen, most manpower gets consumed by food, clothing, and shelter, leaving no time to use science to make things efficient. To accelerate this, the big imperatives are the development of science and the growth of population. Together, these multiply to give us breathing room. For example, if we could obtain grain with twice the scientific efficiency, then by doubling the population, half of the people would be surplus. In that case, civilization would head toward recovery at an accelerating pace. Conversely, if you can't increase manpower, daily life will take all you have, and rebuilding will take an awfully long time. There's another reason the amount of population is necessary for rebuilding. It's that human knowledge is collective. The volume of knowledge and experience in modern science is enormous. No single person can grasp it all and carry things forward, and it would be overwhelmingly inefficient. Rather, it's advantageous to divide up into fine-grained areas of expertise. Accordingly, the knowledge humans have today is collectively designed. The more the population grows, the more the fields of division of labor are subdivided, and the more advanced they become. This, then, is the reason for scientific advancement today. As I mentioned earlier, most modern books actually aren't useful. You could say that today's knowledge, right after Reconstruction starts, won't be of immediate use. What is useful is what you learn in elementary and junior high school: basic science, mathematics, and history. Even if you take a book and read up on an extremely specialized technology, you can't just go and rebuild it right away. Most modern science and technology are things that cannot be reproduced without basic technologies. Namely, materials, tools, machine tools, advanced measurement instruments, and the like. For example, iron, plastics, paper and cloth, laboratory supplies, in manufactured goods, lathes and drills, adhesives and building materials, microscopes and measuring instruments, and without these you can produce almost nothing. For example, even just knowing the temperature or measuring length is incredibly hard. So, in the early stage of rebuilding civilization, it seems efficient to nail down inventions and technologies that had large historical impact. Next, I'd like to talk about agriculture. Nitrogen, phosphorus, and potassium needed for farming are basically contained in the soil. But if you plant on the same soil repeatedly, those elements are depleted, and eventually crops won't grow well enough. So, you need to recycle things like excreta and cycle them as fertilizer. However, with such a production system, not only does recycling incur costs, you also hit a limit on the area you can cultivate. What maintains crop productivity is thorough ecosystem management with potent herbicides, pesticides, and chemical fertilizers. Without these, you can't procure food at the same level, and in a sense, modern agriculture makes crops by feeding on oil. In fact, to produce 1 calorie of food, it's said you end up using about 10 calories worth of oil energy. We're not eating oil directly, but it means we're making food using 10 times as much oil. In a situation where there is nothing, as I said earlier, nearly all human effort will be taken up by farming. Agriculture thus becomes the industry that should be made efficient as quickly as possible. By the way, today, you can produce grain for 10 people on 2 hectares. In modern times, that works out to 1 person producing for 100 people. But first, right after Reconstruction, we'd want to push quickly to the point where 1 person produces food for 10 people. As for food preservation, we'll build systems for stockpiling by various methods: smoking, salting, freeze-drying, and so on. This part is fairly easy to realize. I'd like to talk about thermal power and organic materials, Oil is an important element for an early-stage civilization. As I said earlier, we can assume oil that's easy to obtain no longer exists. That said, there's no problem. Whether we use oil or wood, in the end, there's no big difference. That's because we can see the goal of civilization. In short, while oil is convenient in the early stage for efficiently refining fuel or making materials from crude, once mechanization advances, even if we procure fuel from wood, it won't cost manpower. Rather, acquiring sustainable energy sources that can be produced indefinitely is the future we, living today, should aim for. Incidentally, 3 kilograms of wood are said to be equivalent to 1 kiloliter of gasoline. It means we can leap over the intermediate stage of petrochemicals. Precisely because oil isn't readily available, that choice becomes possible. In the beginning, producing charcoal in large quantities to secure a stable heat source will do. Most materials derived from oil can be substituted with wood. Beyond that, thermal energy is indispensable in all sorts of situations: smelting metals, making salt, firing pottery, cooking, sterilization. Heat processing is essential everywhere. About power. Using wood-fired heat, we build boilers and construct power sources. We boil water in iron pots to make steam. At first, it will probably be steam engines, and if we ignore efficiency, simple steam turbines might also do. Power can be applied to many things: stirring something, digging wells, pumping water. It also helps maintain fires to make materials like iron. Put wheels on that boiler, and it can play an important role in agriculture. The history of using things like livestock for labor or locomotion will likely disappear. Power from water and wind will probably come after life has stabilized. We can't adopt sources that aren't stable as power, and their installation sites are limited, so there's simply no reason to choose them. When electricity becomes necessary, we'll build dams, and then for the first time, generate power with water wheels or turbines. About communications technology, look at developing countries. Unlike Japan, with wired networks throughout the nation, in developing countries, wireless networks spread rapidly over just a few years. I think this wireless network will be the impetus that greatly changes the shape of civilization when we rebuild it. That there's meaning in being able to get this right away. In any case, wireless communication isn't that technically difficult, and long-distance communication has been, in the history we know, one of the most impactful and important innovations. What stands out are its simplicity and overwhelmingly low cost. Compared with wired, the amount of equipment, the costs, and the time to build are on a completely different level. Up to here are the key technologies that should be restored in the early phase of rebuilding civilization. At the beginning I mentioned the Industrial Revolution. The question is, what causes a scientific civilization to arise? In fact, around the 14th century, China was about 1,500 years ahead of Europe. That's how big the gap was. Europe, compared with China, could be called a region quite backward in civilization. From the 15th to the 17th century, Europe entered the Age of Discovery, and from the Industrial Revolution in 18th century Britain, scientific civilization developed at a tremendous speed. Meanwhile, China's scientific civilization stagnated for hundreds of years, to the point that many technologies were lost. This suggests that once a scientific civilization reaches a certain level, it tends to stall. If there's no hunger and safety is secured, people probably have a tendency not to seek further progress. For that reason, China likely stagnated. So why did the Industrial Revolution occur in Britain and Europe at that time? And why did scientific civilization advance so rapidly? Even if the Industrial Revolution was an accelerated development by mechanization, you might think the same revolution could have happened in China 400 years earlier. That implies the Industrial Revolution was triggered by something unrelated to the level of scientific development. That trigger, I think, is why Britain far outstripped China. To be blunt, that trigger wasn't the accumulation of knowledge or technology itself, but the economic environment of Britain at the time. To deliberately use machines instead of the abundant labor that already existed, there had to be commensurate profit. Even in our world today, we have self-checkout. That too is because labor costs exceeded machines. hence the replacement. In short, while labor is cheap, mechanization doesn't advance, so there must be adequate profit. Abundant cheap energy and high-cost labor drive it forward. The high cost of labor was the crucial factor. Britain was in such a situation, and there was a backdrop of capital supply. It was a period when the economic system of capitalists and laborers was developing. Capitalists thus had a strong motivation to replace expensive labor with machines, and so they poured more and more capital into mechanization. Even with the same labor, money increasingly flowed not to human labor, but to the labor of fabrication aimed at mechanization. In China, by contrast, there was no merit in replacing cheap labor with machines. Capital didn't move. It turned out that a capitalist economy played an important role in powerfully pushing forward a scientific civilization. So, in the early phase of rebuilding civilization, do we have to build a capitalist economy at today's level to serve as that trigger? I don't think so. That's because we already know a certain goal. We know what modern science and technology bring. At the same time, we already have a spirit of inquiry, centripetal force towards science and technology. Who in the 18th century could have predicted a highly advanced scientific civilization like today's? Therefore, we can push forward a scientific civilization without necessarily relying on an 18th century British-style capitalist economy. There's something else that is not necessarily needed, or that doesn't arise, in the process of building a civilization. Call it the upside of a civilization reset, the real payoff. That the entrenched vested interests built up over long periods are gone. This is quite important. In modern times, not only radio waves, but the intellectual property created to date belong to those who thought of it or started the business. Patents, intellectual property rights. Basically, most technologies during Reconstruction are ones everyone already knows. In pharmaceuticals, that would be like generics. It's the same logic as not being able to patent something already publicly known. The achievements of science and technology aren't just about bringing convenience. To make things is to design things. With the development of modern information technology, the design philosophies humanity has invented have improved dramatically, not only for industrial products but also for services. We continue to devise advanced design philosophies and methods that thoroughly take sustainability into account. That includes computer virtualization, object orientation, standardization techniques. Put simply, these design philosophies exist to make things that function over the long term. For example, old technologies themselves can hinder new technologies, so you build in mechanisms from the start that let you keep sliding over to newer tech, and the information and software inside computers grow more complex over many years, and they become bottlenecks. It's the same kind of clogging you get from vested interests. Modern information technology addresses this with mechanisms akin to a biological refresh cycle, handling it in a similar way. You design with a refresh cycle woven in from the start. Specifically, I don't currently have an idea to make the economy run on such a mechanism. But with today's irreversible economic systems, we certainly generate a lot of waste. In the early stage of Reconstruction, we can aim to build systems that function long-term and flexibly. In this way, I think it should be possible to create new sustainable, highly scalable economic systems and systems of governance as well. Next, what makes science possible starts with rulers, measuring instruments. Before that, we need scales, units. With standardized metric units and seconds, we can derive all sorts of units. This is extremely handy. You can derive liters and kilograms and the like from the metric system. Mathematics for making accurate predictions is also a very important factor. On science and technology, the operating principles of every technology make use of specific natural phenomena. For example, a clock uses the natural behavior of a pendulum. A swing of a given length takes a fixed time to go back and forth. That's a natural phenomenon. Also, light grows stronger with heat. That too is a natural phenomenon. New technologies always sit atop old ones. The new part of an invention is a combination of existing technologies and components, and its originality and applicability are the very value of the invention. We'll also need various other technologies, so I'll briefly explain them. For instance, building materials, adhesives, mortar, and concrete. One advantage of concrete is that, unlike plaster, it doesn't harden immediately. So if you make wooden forms, you can shape structures freely, and being able to use this from the start is quite powerful, rather than clumsily making all sorts of things from timber. Switching partway to structures that are basically concrete might be better, I think. On place and time. This is pretty important too. For example, what time is it now? Where are we? Those parts actually matter. For clocks, we'd make a pendulum clock. As for calendars, astronomy should suffice. Basically, if you watch the motions of the stars, you can figure out most of the calendar. If at that time we lack the knowledge, we'd observe anew. If you want to know the positions of the stars, for example, you could look at Earth's precession. That sort of thing also makes it possible. For location, you could take some reference and, like a grid, put up signposts every 100 meters. That kind of thing would be an initial task. By the way, if you want to make a clock that tells time small, it needs to be highly accurate. You make one clock somewhere and then you send the time everywhere wirelessly. I think it would be better. Clothing also matters. It's actually pretty important, but I realize making clothes is extremely hard. Not just clothing. Fabric is used in all sorts of things. The nylon fabrics we use today have only about a 70-year history. These synthetic fibers, compared with cotton or wool, are overwhelmingly cheaper and overwhelmingly mass-producible. And today, most inexpensive goods are made by machines. If the machines disappear, everything instantly becomes costly. Woven cloth used for clothing in particular would be produced by hand. Even a fast person takes about 1 second. It takes 1 second to make one row per second. That's the kind of speed. By contrast, nowadays looms can weave at about 100 kilometers per hour. It's incredibly fast.
100 kilometers per hour.
Machines weave at 100 kilometers per hour. We humans have reached something extraordinary. So the current cheap prices are totally different from the true cost of weaving. This part is very tough. Next, printing. Recording and transmission are among the most important elements. Accordingly, paper and pens. These are pretty tough too. Paper is very tricky, pens are tricky, but ink is surprisingly tricky. They require quite a concentration of techniques, so these parts will be tough going. At first we'll settle for just being able to record, but next, printing technology is important. The ability to duplicate what's been recorded matters. To start, we'd use movable type. In other words, letterpress. Type can be made by casting, so we'd like to implement this right away. Next, disease. I think the most dangerous ones are infectious diseases. First, bring public health management up to modern levels. Ready access to water, hand washing, making soap. Even that would change things a lot. Until we can develop medicines like antibiotics, we'd want to minimize deaths with such measures. We might need to perform surgery. Surgery carries great risk. For example, you must keep things sterile, and without a range of conditions aligned, you can't operate. And you need anesthesia. Administering anesthesia without instruments is the worst. The risks are huge, so I don't think it's feasible right away. Explosives also come into play. Explosives useful for mining or hunting could likely be manufactured fairly early if you understand chemistry. They're products of oxidizers. So that's a key set of techniques. And in manufacturing, we should push standardization as early as possible. As I've said many times, science and industry hinge heavily on materials in the background. Leonardo da Vinci, back then, devised all sorts of principles, but I think most of them never reached practical use. In fact, most principles were conceived an awfully long time ago. But we also know that principles alone don't advance technology. That's because the materials needed to put principles into practice, and power sources that don't require human labor, are major factors. And what's crucial in acquiring materials is chemistry. In today's society, so-called chemicals have a very bad reputation. But they're actually extremely important. You often hear things like, "This food contains no artificial chemicals, so it's healthy." But chemicals supplied non-artificially. I haven't seen many of those. Almost every product undergoes some kind of artificial processing or synthesis. Conversely, straight from nature basically doesn't happen. People probably confuse this with petrochemical products, but even oil is a natural substance of biological origin. Civilization lies in achieving qualities desirable for humans and in being able to obtain substances and materials. In this way, chemistry plays an important role in obtaining materials. Burning things or food, neutralization, disinfection, oxidation, these are chemistry. And conversely, to refine metals, we make use of the phenomenon called reduction. Put simply, for iron ore or rust, where iron and oxygen are bonded, you bring in molecules that contain carbon, an element that bonds with oxygen more readily than iron, to strip the oxygen from the iron. Reduction actually occurs at around 400 degrees. If you heat further, it liquefies and reacts uniformly. The reaction accelerates and you can make iron from iron oxide. Cooling systems, and things like boiling and evaporation to make salt, are likewise chemistry. If you know the periodic table, you can logically and systematically invent ways to generate the materials you need. Accordingly, overwhelming, rapid progress becomes possible. Nowadays in elementary school, they have photocells or whatever. Back in my day, it was a manganese battery. Attach wires to a battery and the bulb lights. We did that, right? I think that's the proper form. Now the battery part has become a solar panel. Seeing that, I've wondered what good it is to teach that sort of applied science. I find myself asking whether such a thing can be called an experiment. It's close to a craft project. I didn't think it would let kids engage with real interest. Rather than that, for example, we should teach electromagnetic induction, generating power with a magnet and a coil, storing it with chemicals. Learning about such dry cells would be useful for civilization, reset or survival. So I'd like applied science to be covered in high school or university. If you learn science up through middle school, Science I, you're probably strongest for survival. If the present form of scientific civilization is what has advanced step by step over time, then, as in this case, after civilization disappears, if we build it on the basic knowledge we already have, it may look like a patchwork of techniques. If you picture a civilization shaped by this patchwork of techniques, this is something you often see in anime. It might give rise to something like steampunk, because it would likely become a slightly different, parallel world kind of design. I find that interesting. This time, I've examined it from various angles. If, as a result of such thought experiments, we gain new insights and can spin out outlandish stories, that would be the best experience. Even so, even without rebuilding from one, as in this case, being able to carry on our present civilization while building a more ideal one is something I hope and expect humans can do, and I can't help but feel that way.